Assalamualaikum and a very good day to my seismic wave and imaging lecturer, Dr. Abdul Halim. I hope that you are in a good health. So my name is Ahmad Alias bin Benjamin, a final year, final semester veteran geoscience student with the matrix ID 25498. So my presentation for today aims to answer the extended assignment question 1B, in which it asks to pitch the new innovative seismic migration technique in solving the incoherency of seismic reflection in Figure 1A and Figure 1B of Block PM113 Malay Basin. Before I start answering the question, I would like to explain in brief about the study area, which is the Malay Basin. So Mazlan Madon provided an overview of the structural evolution of the Malay Basin. So the formation of the Malay Basin can be explained by crustal extension model caused by high heat flow or by a more popular extrusion model by Deponier. So he suggested that the extrusion model cannot satisfactorily explain the structural trends of Benue and West Natuna basins. So the tertiary tectonic evolution of the Malay Basin has been widely accepted to comprise three main phases. The three main phases are crustal rifting, followed by basin subsidence, and the compression. So the study concluded that the first phase occurred before the 30 million years ago. The second phase, which is the basin subsidence, was formed 30 million years ago to 14 million years ago, and the third phase lasted from 14 million years ago till the present. First and foremost, what is incoherency? Incoherency is defined as the seismic wave incoherence occurs because of the horizontal and spatial variation of both horizontal and vertical ground motion. There are several features that contribute to the incoherency, such as fault lines, loss of amplitude, and gas cloud. So as observed in the seismic section here, there is a sudden loss of amplitude where it's supposedly to be a continuous layer of high amplitude. Then there are also a sets of faults found in the seismic section that disrupt the continuity of the seismic line. And lastly, there is a presence of gas cloud. The presence of gas cloud gives a chaotic image, which also disrupts the continuity of the seismic image due to wave diffracts because there is a presence of gas. The continuity of reflector also poor seismic when the seismic reflection fluctuates, which in other words is defined as the incoherency. Therefore, the proposed imaging method to improve the incoherency of the block PM113 of Malay Basin is least square migration. What is least square migration? Least square migration is an image enhancement tool. The seismic reflectivity is updated and high graded. Least square migration is a powerful data-driven approach to seismic imaging which aims to recover the Earth through reflectivity by minimizing the misfit between recorded seismic and forward model data. Moreover, it is applicable to all seismic acquisition environments and geometries, including land and ocean bottom. So the goal of least square migration is to update the reflectivity, improve the illumination, and wave number content. So in tackling this problem, the least square migration will try to increase the seismic coherency by making sure that the low coherence image, which is the low amplitude seismic, are as close as possible to the original image, which is the original amplitude seismic, by applying certain acceptable threshold. The process requires numerous amount of iteration and adjustment to produce the final updated image, where the amplitude has been amplified until acceptable threshold. So next is the benefits of least square migration. So least square migration offers many important benefits when compared to conventional migration. So these include reduced migration artifacts and swing noise. It evenly balances the illumination. It improves signal to noise ratio, and it visualizes better event continuity. So with all the benefits that least square migration has, it is a suitable imaging method in order to improve the incoherency of seismic section, block PM113, Malay Basin. So here is the least square migration workflow. So the first step of LSM start with a standard migration. After that, the migrated image will be used as a reflectivity model in bond modeling and create a synthetic data. After that, we will try to compare the differences between the observed data and synthetic data. So if the differences are large and not within the range of acceptable threshold, then the differences will be migrated and used to update the image and form a new updated image. So when the differences between observed and synthetic image is acceptable, then it will form the final image. Here is the advancement of knowledge of least square migration as it transfers from the forward modeling to the reverse time migration and lastly to the least square migration. So it all started with the forward modeling where the data D computed by applying the acoustic forward modeling operator L to the velocity model M to get D equal to L times M. But a better way to increase the visualization instead of that is by doing the transpose of the linearized forward modeling operator, which leads to the reverse time regression. So for the RTM equation, the L transpose is applied to the observed seismic data D and give the RTM image. Again, instead of computing an image at L transpose, we can get a better image with least square migration LSM. As you can see in the LSM formula, it is similar to the RTM formula but with the addition of the inverse Hessian. So to solve this equation, we cannot store and compute the inverse Hessian. So what we do instead is pursuing the iterative solution by solving this optimization problem. We are trying to minimize with respect to reflectivity model M that the difference between predicted and observed data predicted given by LM and observed data D. So for the presentation quality, the figure on the left is the unmigrated section, meanwhile the right figure is the migrated section. So as you can observe, in the unmigrated section, the dipping events are not properly positioned. Also, the deflection events are not collapsed and they are overlapping events. Meanwhile, dipping events in migrated section is properly positioned and there is a collapsing of diffraction event. You can also observe that there is no event crossing in the migrated section. As observed here, it shows the difference between the RTM and the LSM. So in RTM image, the features, the amplitudes are not well balanced and the image is not well focused, especially in a greater depth. Meanwhile, in least square migration, the amplitude are well balanced, the reflectors are better focused. So to conclude my presentation for today, least square migration is a perfect method in solving the incoherency problems that are faced by seismic section in PM1311 Malay Basin, as it is able to enhance the subsurface image clearly and improve the continuity of the seismic image. That is all for my presentation today. I thank you, Dr. Halem, for spending your time to assess this presentation. I end my presentation with Assalamualaikum warahmatullahi wabarakatuh and have a good day.